Welcome to week 1 of our 52-week program. This is actually going to be presentation 1 of possibly 3 for week 1. So you want to try to find parts 2 and 3 also. And again, just a reminder, all these presentations are available in PDF format on my website as PDF handouts. So week 1 is extremely important because it's the introduction to electrical. Okay, and to be successful in the field, week 1 material needs to be second nature to you. I'm going to say the same thing for week 2 and week 3. This presentation is going to talk about electronics, electricity, characteristics of electricity, Ohm's law, and Watt's law. It provides a foundation for everything else. So what is electricity? Okay, electricity is delivered to us on power lines when there's power lines available, comes through our breaker panel over there on the right-hand side, and then gets delivered to appliances like our gas furnace. Okay, that's what the average person knows about electricity. Electronics is part of your everyday job. 90% of the problems you encounter will be electrical. You will not understand anything else if you do not understand basic electrical. Okay, electronics is a study of the movement of electricity through wires, switches, and loads. Electricity is a fundamental element of nature. Electricity starts with an atom consisting of an electron and a proton. The electrons jump from atom to atom. Okay. Atoms are made of particulars called protons, neutrons, and electrons. Protons have a positive charge. Electrons have a negative charge. Neutrons have no charge and therefore have no electrical effect. The movement of the electrons, because remember they jump from atom to atom, creates electrical current. With the use of a proper conductor, the current will move in a controllable manner and become usable. Electricity is produced by one of 4 methods. Friction creates static electricity. Chemically is how electricity is produced in a battery. Magnetism is how electricity is produced in a power plant or generator. Mechanically is how electricity is produced in a thermocouple. We'll talk about that when we talk about gas heating. The imbalance of electrons is called a potential difference or electromotive force, EMF. A potential difference, again, can be created by friction, chemical, magnetic, thermoelectric, or photoelectric. Thermoelectric is heat, photoelectric is light. The unit of measurement of EMF is the volt. An electromotive force is one that's created by a magnet spinning inside wires. The current that is generated by the spinning magnet is sent over the wires to do work. This is power, voltage, and amperage. Okay, voltmeters are used to measure potential differences between 2 specific points. Voltmeters are available in analog or digital types. The voltmeter measures the difference, okay, a potential difference from one point to another. Okay, there must be a potential difference for the meter to register a voltage reading, and we'll talk more about meters in the future. Okay, so if you take a look at the circuit on the left, okay, there's no difference because there's an open switch. And again, we have to talk more about this, but everything is on the neutral side of the circuit because there's an open switch going to the 120 volts. Across 120 to the same side of the load, again, there's no potential difference. Okay, there's no difference between the 2 probes, which you have to be careful about. Okay, because a broken wire condition like this, okay, could actually read the same potential, no difference, but there's voltage present. So you do have to be careful about this. Current is the movement of electrons. Current is measured and recorded in amps, okay, usually using an amp clamp such as this that I'm using in these pictures. 2 types of currents are used in the HVAC industry. You have direct current, which is DC, and you have alternating current, which is AC. Current is the flow of electrons. DC current is an electron flow only in one direction. AC current, or alternating current, is back and forth flow of electrons, which means the electrons reverse their direction of flow at regular intervals. DC current has not been as common as AC, and it is only used in certain applications. However, having said that, DC is gaining popularity with higher efficiency motors. Motors can be made to run way more efficient by using DC current. Most of the current produced by electric utilities is alternating current. Most of the equipment in the HVAC industry runs on alternating current, as do most of the items in your home. One of the benefits to AC current is money. It is cheaper and more trouble-free than equipment that runs on DC current. However, within the next couple years, that is going to change. So that by the time you're through your apprenticeships, through your training, that's going to change. Since AC is the most widely used form of current, we need to understand the theory behind how it works, and we should be familiar with the way it's distributed by the power companies. So alternating current, AC, is electron flow that alternates. Electricity flows in one direction and then in the opposite direction at regular intervals. AC current is produced by cutting a magnetic field with a conductor. The sine wave is used as a graphical representation of AC current. This is a sine wave. One wave cycle starts at 0, goes through 180, comes back to 360 degrees. So if you actually put the sine waves together and flip the 180 to 360 around, it would almost be a complete circle. One wave cycle is from 0 to 360, 270 to 270, okay? As long as it makes a complete rotation, it's one wave cycle. When a conductor rotates through one complete revolution, it has generated two alternations or flow reversals. Two alternations, just like we showed in the diagram, is one cycle. One cycle occurs when the rotor or conductor cuts the magnetic field of a north and south pole. The frequency of AC is the number of complete cycles that occur in a second. Frequency is known as hertz, but it can also be referred to as cycles. The most common frequency in the United States is 60 hertz, but in some other areas and in foreign countries, 25 or 50 hertz is used. A 25 hertz circuit can be detected by human eye in light fixtures. A 60 hertz frequency is most common, but 50 hertz is used in Europe. The phase of AC circuits is the number of currents alternating at different times in the circuit. Single phase only has one current. Three phase has three separate currents. Alternating current is available in different voltages with different current characteristics. You could have 230 single phase 60 hertz. You could have 230 three phase 60 hertz. You could have 208 three phase and 460 three phase. This is an example of a sine wave for a three-phase circuit. You have phase 1, you have phase 2, and you have phase 3. We're going to talk much more about this in more detail in the future, but just be aware that three-phase circuits do exist. Okay, most residential and light commercial will use single phase. This is a single phase. Okay, now effective voltage or RMS voltage is also something we have to talk about. Because AC starts at 0, reaches a peak, then returns to 0, there's always a variation in voltage, and an effective voltage has to be determined. AC current reaches its peak at about 90 degrees. This is known as peak voltage. The effective voltage is 0.707 times its highest or peak voltage. AC amperage is also 0.707 times the peak voltage. In other words, your effective voltage, RMS voltage, is going to be slightly less than peak voltage. All electrical meters are calibrated to read effective voltage and effective amperage. AC current, as we said, is produced by an alternator. An alternator is made up of windings, or a set of windings called the stator, and a rotating magnet called the rotor. The number of windings used depends on the desired phase characteristics of the current. When the rotor is rotated through the field of the winding, an alternating electrical current is produced. Okay, this is an example of a single-phase current. Okay, single-phased alternator. In other words, a generator. That's what all an alternator is. One winding on the stator. Three-phase current is produced by an alternator with three windings in the stator that are wound 120 degrees apart. 3 times 120 is 360. There we come back to our nagging 360-degree circle. Amperage, also known as ampere, amperage, amps, and current, are terms used to describe the quantity and the intensity of the electrons moving through a conductor. When current flows through a conductor, a magnetic field is created. The clamp-on ammeter is most commonly used on AC circuits. Resistance. Okay, resistance is another term. Electron flow is energy in motion and has to be controlled. Resistance refers to anything offering opposition to the current flow. There are several types of resistances that will be discussed, but a basic understanding of Ohm's law is necessary before that discussion. Pure resistance is constant, such as the heating element in a light bulb. Inductive reactance is another type of resistance that's caused by a magnetic field that develops around a conductor, especially in coils or motor. Capacitive reactances use a device called capacitors to store and discharge electrons that create an opposition to current flow. The total of the pure resistance, inductive reactance, and capacitive reactance is called impedance. To measure resistance, we use an ohm meter. Batteries inside the meter provide a power supply to measure the electron movement. We never connect an ohm meter to a circuit with the power on, or you won't have a meter left. Damage to the meter may occur. Also be sure that the component you are measuring is disconnected to prevent a feedback circuit and false readings. Components have to be isolated to get good resistances. Resistance can be calculated on live circuits by measuring voltage and amperage, and then using Ohm's law, which is voltage divided by amperage, to find the resistance. Again, measuring resistance, we're going to use our ohm meter, set it to ohms or resistance, and you're going to isolate the component. You'll see that this compressor on the right side is isolated. There's no other wires going to it, so we can get a good resistance. AC circuits are affected by resistance, but they're also affected by reactance. Reactance, as I mentioned earlier, is the resistance that AC encounters when it changes flow. Two types of reactance, inductive reactance and capacitive reactance. I've repeated this a couple times, so it's probably important to remember it. It's a common assumption that when voltage is at its strongest, amperage is also at its strongest. This is not always the case. Amperage of the circuit determines the strength of the magnetic field in the circuit. If the current increases, so will the magnetism. And if the current decreases, the magnetism will decrease as well. The fluctuation of the magnetic strength of an AC circuit and in conductors induces a voltage that counteracts the original voltage. This effect is called inductance. The inductance of an AC circuit is effectively the magnetic field. It produces an out-of-phase condition between voltage and amperage. Inductive reactance is the opposition to the change of flow of the current, which produces an out-of-phase condition between voltage and amperage. Capacitive reaction is caused in AC circuits by using capacitors. When a capacitor is put in AC circuit, it resists the change in voltage, causing the amperage to lead the voltage. The sum of the resistance and reactance in an AC circuit is called impedance. Ohm's law is the relationship between voltage, amperage, and resistance. The formula for Ohm's law is E equals I times R. And again, E is voltage, I is amperage, and R is resistance. Therefore, if any two values are known, you can solve the equation to find the other. Okay? Ohm's law pie chart is extremely important. Okay? If it's above like in the top diagram, if E is above I or E is above R, you divide. If they're next to each other, like I and R are, you multiply. So you cover E, that's the number you want to find in the red side, in the last circle over there. You cover the one you want to find, and the two remaining are the formula. So if you cover E, you get I times R. If you cover R, you get E divided by I. If you cover I, you get E divided by R. These circles are pretty important to know and be able to just jot down or have memorized if you ever need them. There's also a thing called wheel of electricity, okay, where you can find any of the center letters. I is amperage, R is resistance, E is voltage, W is power. Okay, if you know any of the two other values. This one I don't expect you to memorize, but the others I do. Power, okay, is also an important term. It's W in Ohm's law because it's watts. Since voltage and current are out of phase with each other in an AC circuit, they're not working together. Thus, power of a circuit must be calculated using a voltmeter and an ammeter. Power is calculated in watts. Electrical power is the rate at which electricity is used to perform useful work. The work performed is measured in units called watts. Watts are calculated by multiplying amperage times voltage. So W equals I times E. 746 watts is equal to 1 horsepower. Watt's law is the relationship between power, current, and voltage. 1 watt is 1 amp at 1 volt. 1 watt hour is 1 watt used in 1 hour. The power company bills you on watt hours, or most likely kilowatts per hour. The ratio between true power and apparent power is called the power factor. The power factor is usually expressed in percentages. The formula here can be used to calculate the power factor for a circuit. So true power is measured, divided by apparent power, which is calculated, is power factor. So in this presentation, we've talked about amperages, we've talked about resistance, we've talked about voltage, we've talked about what electricity is. We've given a little bit of an introduction to Ohm's law. In the next presentation, we're going to move on a bit and we're going to talk about circuits, diagrams, and series and parallel circuits and combination circuits.